Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Big Bang. The Big Bang Theory is the prevailing cosmological model explaining the existence of the observable universe from the earliest known periods through its subsequent large-scale evolution. The model describes how the universe expanded from an initial state of high density and temperature and offers a comprehensive explanation for a broad range of observed phenomena, including the abundance of light elements, the cosmic microwave background (CMB) radiation, and large-scale structure. Crucially, the theory is compatible with Hubble-Lemaitre law, the observation that the farther away a galaxy is, the faster it is moving away from Earth. Extrapolating this cosmic expansion backwards in time using the known laws of physics, the theory describes an increasingly concentrated cosmos preceded by a singularity in which space and time lose meaning, typically named the Big Bang singularity. Detailed measurements of the expansion rate of the universe place the Big Bang singularity at around 13.8 billion years ago, which is thus considered the age of the universe. After its initial expansion, an event that is by itself often called the Big Bang, the universe cooled sufficiently to allow the formation of subatomic particles and later atoms. Giant clouds of these primordial elements, mostly hydrogen with some helium and lithium, later coalesced through gravity, forming early stars and galaxies, the descendants of which are visible today. Besides these primordial building materials, astronomers observe the gravitational effects of an unknown dark matter surrounding galaxies. Most of the gravitational potential in the universe seems to be in this form, and the Big Bang theory and various observations indicate that this excess gravitational potential is not created by baryonic matter, such as normal atoms. Measurements of the redshifts of supernovae indicate that the expansion of the universe is accelerating, an observation attributed to dark energy's existence. Georges Lemaitre first noted in 1927 that an expanding universe could be traced back in time to an originating single point, which he called the primeval atom. Edwin Hubble confirmed through analysis of galactic redshifts in 1929 that galaxies are indeed drifting apart. This is important observational evidence for an expanding universe. For several decades, the scientific community was divided between supporters of the Big Bang and the rival steady-state model, which both offered explanations for the observed expansions. But the steady-state model stipulated an eternal universe, in contrast to the Big Bang's finite age. In 1964, the CMB was discovered, which convinced many cosmologists that the steady-state theory was falsified, since, unlike the steady-state theory, the hot Big Bang predicted a uniform background radiation throughout the universe, caused by the high temperatures and densities in the distant past. A wide range of empirical evidence strongly favors the Big Bang, which is now essentially universally accepted. Features of the model. The Big Bang theory offers a comprehensive explanation for a broad range of observed phenomena, including the abundances of the light elements, the CMB, large-scale structure, and Hubble's law. The theory depends on two major assumptions: the universality of physical laws and the cosmological principle. The universality of physical laws is one of the underlying principles of the theory of relativity. The cosmological principle states that on large scales, the universe is homogeneous and isotropic, appearing the same in all directions regardless of location. These ideas were initially taken as postulates, but later efforts were made to test each of them. For example, the first assumption has been tested by observations showing that largest possible deviation of the fine structure constant over much of the age of the universe is of order 10 to the negative fifth. Also, general relativity has passed stringent tests on the scale of the solar system and binary stars. The large-scale universe appears isotropic as viewed from Earth. If it is indeed isotropic, the cosmological principle can be derived from the simpler Copernican principle, which states that there is no preferred or special observer or vantage point. To this end, the cosmological principle has been confirmed to a level of 10 to the negative fifth via observations of the temperature of the CMB. At the scale of the CMB horizon, the universe has been measured to be homogeneous, with an upper bound on the order of 10% inhomogeneity as of 1995. Expansion of space. The expansion of the universe was inferred from early 20th century astronomical observations and is an essential ingredient of the Big Bang theory. Mathematically, general relativity describes space-time by a metric, which determines the distances that separate nearby points. The points, which can be galaxies, stars, or other objects, are specified using a coordinate chart or grid that is laid down over all space-time. The cosmological principle implies that the metric should be homogeneous and isotropic on large scales, which uniquely singles out the Friedmann-Lemaitre-Robertson-Walker FLRW metric. This metric contains a scale factor which describes how the size of the universe changes with time. This enables a convenient choice of a coordinate system to be made called co-moving coordinates. In this coordinate system, the grid expands along with the universe, and objects that are moving only because of the expansion of the universe remain at fixed points on the grid. While their coordinate distance, co-moving distance, remains constant, the physical distance between two such co-moving points expands proportionally with the scale factor of the universe. The Big Bang is not an explosion of matter moving outward to fill an empty universe. Instead, space itself expands with time everywhere and increases the physical distances between co-moving points. In other words, the Big Bang is not an explosion in space, but rather an expansion of space. Because the FLRW metric assumes a uniform distribution of mass and energy, it applies to our universe only on large scales. Local concentrations of matter, such as our galaxy, do not necessarily expand with the same speed as the whole universe. Horizons. An important feature of the Big Bang space-time is the presence of particle horizons. Since the universe has a finite age and light travels at a finite speed, there may be events in the past whose light has not yet had time to reach us. This places a limit or a past horizon on the most distant objects that can be observed. Conversely, because space is expanding and more distant objects are receding ever more quickly, light emitted by us today may never catch up to very distant objects. This defines a future horizon, which limits the events in the future that we will be able to influence. The presence of either type of horizon depends on the details of the FLRW model that describes our universe. Our understanding of the universe back to very early times suggests that there is a past horizon, though in practice our view is also limited by the opacity of the universe at early times. So our view cannot extend further backward in time, though the horizon recedes in space. If the expansion of the universe continues to accelerate, there is a future horizon as well. Thermalization. Some processes in the early universe occurred too slowly, compared to the expansion rate of the universe, to reach approximate thermodynamic equilibrium. Others were fast enough to reach thermalization. The parameter usually used to find out whether a process in the very early universe has reached thermal equilibrium is the ratio between the rate of the process, usually rate of collisions between particles, and the Hubble parameter. The larger the ratio, the more time particles had to thermalize before they were too far away from each other. Timeline. According to the Big Bang theory, the universe at the beginning was very hot and very compact, and since then it has been expanding and cooling down. Singularity. Extrapolation of the expansion of the universe backwards in time using general relativity yields an infinite density and temperature at a finite time in the past. This irregular behavior, known as the gravitational singularity, indicates that general relativity is not an adequate description of the laws of physics in this regime. Models based on general relativity alone cannot extrapolate towards the singularity before the end of the so-called Planck epoch. This primordial singularity is itself sometimes called the Big Bang, but the term can also refer to a more generic early hot, dense phase of the universe. In either case, the Big Bang as an event is also colloquially referred to as the birth of our universe, since it represents the point in history where the universe can be verified to have entered into a regime where the laws of physics, as we understand them, specifically general relativity and the standard model of particle physics, work. Based on measurements of the expansion using type-Lanove and measurements of temperature fluctuations in the cosmic microwave background, the time that has passed since that event, known as the age of the universe, is 13.8 billion years. Despite being extremely dense at this time, far denser than is usually required to form a black hole, the universe did not recollapse into a singularity. Commonly used calculations and limits for explaining gravitational collapse are usually based upon objects of relatively constant size, such as stars, and do not apply to rapidly expanding space, such as the Big Bang. Since the early universe did not immediately collapse into a multitude of black holes, matter at that time must have been very evenly distributed with a negligible density gradient. Inflation and baryogenesis. The earliest phase of the Big Bang are subject to much speculation, since astronomical data about them are not available. In the most common models, the universe was filled homogeneously and isotropically, with a very high energy density and huge temperatures and pressures, and was very rapidly expanding and cooling. The period from 0 to 10 to the negative 43rd seconds into the expansion, the Planck epoch, was a phase in which the four fundamental forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, and the gravitational force, were unified as one. In this stage, the characteristic scale length of the universe was the Planck length, 1.6 times 10 to the negative 35th meters, and consequently had a temperature of approximately 10 to the 32 degrees Celsius. Even the very concept of a particle breaks down in these conditions. A proper understanding of this period awaits the development of a theory of quantum gravity. The Planck epoch was succeeded by the Grand Unification epoch beginning at 10 to the negative 43 seconds, where gravitation separated from the other forces as the universe's temperature fell. At approximately 10 to the negative 37 seconds into the expansion, a phase transition caused a cosmic inflation, during which the universe grew exponentially, unconstrained by the light speed invariance, and temperatures dropped by a factor of 100,000. Microscopic quantum fluctuations that occurred because of Heisenberg's uncertainty principle were amplified into the seeds that would later form the large-scale structure of the universe. At a time around 10 to the negative 36 seconds, the electroweak epoch begins when the strong nuclear force separates from the other forces, with only the electromagnetic force and weak nuclear force remaining unified. Inflation stopped at around 10 to the negative 33 to 10 to the negative 32 seconds mark, with the universe's volume having increased by a factor of at least 10 to 78. Reheating occurred until the universe obtained the temperatures required for the production of a quark-gluon plasma, as well as all other elementary particles. Temperatures were so high that the random motions of particles were at relativistic speeds, and particle-antiparticle pairs of all kinds were being continuously created and destroyed in collisions. At some point, an unknown reaction called baryogenesis violated the conservation of baryon number, leading to a very small excess of quarks and leptons over antiquarks and antileptons of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter in the present universe. Cooling. The universe continued to decrease in density and fall in temperature, hence the typical energy of each particle was decreasing. Symmetry-breaking phase transitions put the fundamental forces of physics and the parameters of elementary particles into their present form, with the electromagnetic force and weak nuclear force separating at about 10 to the negative 12 seconds. After about 10 to the negative 11 seconds, the picture becomes less speculative, since particle energies drop to values that can be attained in particle accelerators. At about 10 to the negative 6 seconds, quarks and gluons combine to form baryons, such as protons and neutrons. The small excess of quarks over antiquarks led to a small excess of baryons over antibaryons. The temperature was no longer high enough to create either new proton-antiproton or neutron-antineutron pairs. A mass annihilation immediately followed, leaving just 1 in 10 to the 8th of the original matter particles and none of their antiparticles. A similar process happened at about 1 second for electrons and positrons. After these annihilations, the remaining protons, neutrons, and electrons were no longer moving relativistically, and the energy density of the universe was dominated by photons, with a minor contribution from neutrinos. A few minutes into the expansion, when the temperature was about 1 billion Kelvin, and the density of matter in the universe was comparable to the current density of Earth's atmosphere, neutrons combine with protons to form the universe's deuterium and helium nuclei in a process called Big Bang nucleosynthesis, BBN. Most protons remained uncombined as hydrogen nuclei. As the universe cooled, the rest energy density of matter came to gravitationally dominate that of the photon radiation. After about 379,000 years, the electrons and nuclei combined into atoms, mostly hydrogen, which were able to emit radiation. These relic radiation, which continued through space largely unimpeded, is known as the cosmic microwave background. Structure formation. Over a long period of time, The slightly denser regions of the uniformly distributed matter gravitationally attracted nearby matter, and thus grew even denser, forming gas clouds, stars, galaxies, and the other astronomical structures observable today. The details of this process depend on the amount and type of matter in the universe. The four possible types of matter are known as cold dark matter, warm dark matter, hot dark matter, and baryonic matter. The best measurements available from the Wilkinson Microwave Anisotropy Probe, WMAP, show that the data is well fit by a lambda CDM model, in which the dark matter is assumed to be cold, warm dark matter is ruled out by early reionization, and is estimated to make up about 23% of the matter energy of the universe, while baryonic matter makes up about 4.6%. In an extended model, which includes hot dark matter in the form of neutrinos, then if the fission baryon density is estimated at about 0.023, this is different from the baryon density expressed as a fraction of the total matter energy density, in which is about 0.46. Cosmic acceleration. Independent lines of evidence from type 1a supernova and the CMB imply that the universe today is dominated by a mysterious form of energy, known as dark energy, which apparently permeates all of space. The observations suggest 73% of the total energy density of today's universe is in this form. When the universe was very young, it was likely infused with dark energy, but with less space and everything closer together. Gravity predominated, and it was slowly breaking the expansion. But eventually, after numerous billion years of expansion, the declining density of matter relative to the density of dark energy caused the expansion of the universe to slowly begin to accelerate. Dark energy in its simplest formulation takes the form of the cosmological constant term in Einstein field equations of general relativity. But its composition and mechanism are unknown, and more generally, the details of its equation of state and relationship with the standard model of particle physics continue to be investigated both through observation and theoretically. All of this cosmic evolution after the inflationary epoch can be rigorously described and modeled by the ACDM model of cosmology, which uses the independent frameworks of quantum mechanics and general relativity. There are no easily testable models that would describe the situation prior to approximately 10 to the negative 15 seconds. Understanding this earliest of eras in the history of the universe is currently one of the greatest unsolved problems in physics. History. Etymology. English astronomer Fred Hoyle is credited with coining the term Big Bang during a talk for a March 1949 BBC radio broadcast, saying, "These theories were based on the hypothesis that all the matter in the universe was created in one Big Bang at a particular time in the remote past." However, it did not catch on until the 1970s. It is popularly reported that Hoyle, who favored an alternative, steady-state cosmological model, intended this to be pejorative, but Hoyle explicitly denied this and said it was just a striking image meant to highlight the difference between the two models. Helge Krafft writes that the evidence for the claim that it was meant as a pejorative is unconvincing, and mentions a number of indications that it was not a pejorative. The term itself is a misnomer, as it implies the occurrence of an explosion. However, an explosion implies expansion from a center point out into the surrounding space, which did not yet exist. Rather than exploding into space, the Big Bang was the expansion, stretching of space itself, which is a much harder concept to grasp. Another issue pointed out by Santosh Mathew is that bang implies sound, which would require a vibrating particle and medium through which it travels. Since this is the beginning of anything we can imagine, there is no basis for any sound, and thus the Big Bang was likely silent. An attempt to find a more suitable alternative was not successful. Development. The Big Bang theory developed from observations of the structure of the universe and from theoretical considerations. In 1912, Vesto Slipher measured the first Doppler shift of a spiral nebula. Spiral nebula is the obsolete term for spiral galaxies, and soon discovered that almost all such nebulae were receding from Earth. He did not grasp the cosmological implications of this fact, and indeed at the time it was highly controversial whether or not these nebulae were island universes outside our Milky Way. 10 years later, Alexander Friedmann, a Russian cosmologist and mathematician, derived the Friedmann equations from Einstein field equations, showing that the universe might be expanding in contrast to the static universe model advocated by Albert Einstein at that time. In 1924, American astronomer Edwin Hubble's measurement of the great distance to the nearest spiral nebulae showed that these systems were indeed other galaxies. Starting that same year, Hubble painstakingly developed a series of distance indicators, the forerunner of the cosmic distance ladder, using the 100-inch Hooker telescope at Mount Wilson Observatory. This allowed him to estimate distances to galaxies whose redshifts had already been measured, mostly by Slipher. In 1929, Hubble discovered a correlation between distance and recessional velocity, now known as Hubble's law. By that time, Lemaitre had already shown that this was to be expected, given the cosmological principle. Independently deriving Friedmann's equation in 1927, Georges Lemaitre, a Belgian physicist and Roman Catholic priest, proposed that the inferred recession of the nebula was due to the expansion of the universe. In 1931, Lemaitre went further and suggested that the evident expansion of the universe, if projected back in time, meant that the further in the past, the smaller the universe was, until at some finite time in the past, all the mass of the universe was concentrated into a single point, a primeval atom, where and when the fabric of time and space came into existence. In the 1920s and 1930s, almost every major cosmologist preferred an eternal steady-state universe, and several complained that the beginning of time implied by the Big Bang imported religious concepts into physics. This projection was later repeated by supporters of the steady-state theory. This perception was enhanced by the fact that the originator of the Big Bang theory, Lemaitre, was a Roman Catholic priest. Arthur Eddington agreed with Aristotle that the universe did not have a beginning in time, that matter is eternal. A beginning in time was repugnant to him. Lemaitre, however, disagreed. If the world has begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have a sensible meaning when the original quantum had been divided into a sufficient number of quanta. If this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. During the 1930s, other ideas were proposed as non-standard cosmologies to explain Hubble's observations, including the Milne model, the oscillatory universe, originally suggested by Friedmann, but advocated by Albert Einstein and Richard C. Tolman, and Fritz Zwicky's tired light hypothesis.